video we will see a problem of slope and deflection which we are going to solve by using double integration method. Here is the question. A simply supported beam of span 9 meter carries 2 point loads, 210 kilonewton and 125 kilonewton at 2 meter and 6 meter from left support. The self weight of the beam is 26 kilonewton per meter. Determine maximum slope and deflection at the center. EI is a constant. So here in the data, we have to find out the maximum slope. Maximum slope is denoted by dy by dx. So we have to find out the maximum value of dy by dx. And deflection, it is denoted by y at the center, and it is given that EI is constant. So now, with the data available, let us try to get the solution to this problem. Now, here in the solution part, the first thing is I'll draw the diagram with the data which is given. Now they are saying that a simply supported beam of span 9 meter. So here we have a simply supported beam whose span is 9 meter. Next, carries 2 point loads, 210 kilonewton and 125 kilonewton at 2 meter and 6 meter from left support. So the first load, which is 210 kilonewton, is at 2 meter distance from left support. So from the left hand side support, at 2 meter distance, there is a point load of 210 kilonewton given. Next, 125 kilonewton is at 6 meter from left support. So here I am marking the distances and indicating the load. So 6 meter from the left hand support, we have a load of 125 kilonewton. Now here I'll denote this as points C and D. Next, the self weight of the beam is 26 kilonewton meter. Now the self weight of the beam, is nothing but it is called as uniformly distributed load. So the self weight of the beam is shown in the form of uniformly distributed load, and that uniformly distributed load, it has a value of 26 kilonewton per meter as the intensity. So now this is the diagram of the beam, and for such a beam we have to find out the maximum slope and deflection at the center. So when we are solving such problems based on double integration method, the first thing is we should know the support reactions. At A, the reaction will be R suffix A, at B it will be R suffix B. So while writing the solution, I'll say that since summation of Fy is equal to 0, considering the beam to be in equilibrium, here I'll take upward forces as positive and downward forces as negative. So therefore here I have RA and RB as positive, so RA plus RB minus 210 minus 125 minus now 26 into 9, because I have to convert it into point load, so this UDL will be converted into point load. 26 into 9, and that comes out to be 234. It's equal to 0. So therefore, when I add up RA plus RB, it comes out to be 569. Now I'll keep this as equation number 1. Next, now I want to calculate RA, so I'll be taking the moments at point B. So therefore, summation of moments about point B is equal to 0. Here, clockwise moment will be treated positive, anti-clockwise moment as negative. So therefore, here I have RA into 9 as clockwise, then 210 into this remaining distance is 7, so minus 210 into 7. Next, 125, again this is anti-clockwise, 125 into this remaining distance is 3 meter, so minus 125 into 3, and this UDL, it has a value of, we have found out 26 into 9, that came out to be 234. So minus 234 into this UDL will be acting when it is converted into point load at exactly half of the beam, that is 4.5. So minus 234 into 4.5 is equal to 0. So here I'll get RA value, which comes out to be 322 kilonewton. So put RA in equation number 1. So therefore RB value will be 569 minus 322, and it is 247 kilonewton. So here I have found out the support reactions RA and RB. I'll write the values onto this diagram. RA is 322 kilonewton. Next, RB is 247 kilonewton. Now once I have found the support reactions, now we have to solve this problem by using the double integration method. And for that, here I'll say that consider a section XX at a distance small x from left hand support. So here I will be considering a section on this beam which will be from left hand support, and it should be far away from A and close to B. So here I am considering a section, and this is the section X. Which I am considering section XX at a distance small x from left hand support. Now I will be taking moments at this section. So I'll say that after I've taken the section, therefore taking moments of all forces at section XX. So now here I am taking moments of all forces at section XX, and this is done by double integration method, and many a times double integration method is also called as Macaulay's method. So moment at section XX is given by EI d square y by dx square, and that is equal to, now here when I am taking the moment at section XX, I have to consider, or I will consider, or all clockwise moment as positive and anti-clockwise moment as negative. So the first thing is RA into X clockwise. Next we have 210 into, now this distance between 210 and section XX will be X minus 2. x minus 2 will be the distance between two 10 kilonewton force and XX section. So, and it is producing an anticlockwise moment, produces anticlockwise moment at section XX. So here I have minus 210 into x minus 2. Then we have 125. This also produces anticlockwise moment, and the distance between 125 kilonewton and XX section, this is x minus 6. X minus 6. So minus 125 into x minus 6. The next thing is UDL, and for that we have to consider the UDL only up to section X. So the force will be 26 into X, that is the point load, and if I want to take the moment, it will be exactly at half of X, so that becomes minus 26 into X, that gives us the force value, and it will be acting at x by 2 distance. So if I multiply with x by 2, this becomes x square by 2, because 26 into x is the point load, and that point load acts at half of x, that is x by 2. So 26 into x multiplied by x by 2, that gives us minus 26 into x square by 2. Now here we have completed all the forces. Now after reaching this stage, I'll write it again, that EI d square y by dx square is equal to RA value, I'll put it here, which is 322, x minus 210 into x minus 2 minus 125 into x minus 6 and minus 26 by 2 x square. Next, after I have reached here, now I will integrate this equation. So therefore, integrating once we get, because we are using double integration method, so I'll integrate it for the first time and then for the second time. So here I have EI d square y by dx square will become dy by dx. Here it is 322. Integration of x, that is x square by 2 minus 210, x minus 2, that becomes x minus 2 whole square by 2 minus 125, x minus 6 whole square by 2 minus 26 by 2, it is already there, into x cube by, here we have x cube by 3, and here I have to add at the first term. Since I have integrated, I'll add a constant which is c1, so I'll write it in a more better manner. So therefore EI dy by dx will be equal to 322 by 2 x square plus c1. Now this is the first term. Next, minus 210 by 2 into x minus 2 whole square, this will be the second term, minus 125 by 2 into x minus 6 whole square, the third term, and at last we have minus 26 by 6 x cube, because here I have multiplied 2 into 3, that gives us 6. Now I have integrated this equation once, and I will give this as the first equation. Now here I have dy by dx. dy by dx is nothing but, it is called as slope. Next, we are going to integrate this equation number 1 to get the equation of deflection, that is y. So therefore, integrating again, we get EI will remain as it is because it is constant. Dy by dx will be equal to y. Here we have 322 divided by 2 as it is. X square will become x cube by 3. Now plus c1. If I integrate this with respect to x, that will be c1 into x. Since I am integrating for the second time, so I have to add another constant. which is C2 minus 210 by 2. Now here I have x minus 2. It was square, so integration will be cube divided by 3. Then minus 125 by 2. Here we have x minus 6 square, and if I integrate, that becomes cube divided by 3. At last minus 26 by 6 x cube, so that becomes x raised to 4 divided by 4. So here I have integrated it again, then simplifying it, here we have 322, 2 into 3, that is 6 x cube plus c1 into x plus c2, then minus 210, this will be 6, then 2 into 3, that is 6 x minus 6 whole cube minus 26, 6 into 4, that becomes 24 x raised to 4. Now the equation which we have, this will be the second equation, and in this we have y, which is called as deflection. But now when we look at equation 1 and equation 2, in both the equations there are constants c1 and c2, so we need to find out the values of these constants, and that can be calculated by using the boundary conditions. So I'll say that therefore to find constants c1 and c2 using boundary conditions, the first boundary condition, and boundary conditions we have to put in deflection equation, that is in equation number 2. So the first boundary condition will be when x value is 0, that is at point A, the deflection y is 0. So the first thing is at x is equal to 0, y is equal to 0, and here the second boundary condition would be at x is equal to 9 meters, that is at point B, again the deflection is 0. So at x is equal to 9 meter, y is equal to 0. So first I'll put the first boundary condition. So therefore putting first boundary condition in equation second. So we have at the first boundary condition y value is 0, so left hand side becomes 0, it's equal to, now over the right hand side for the first boundary condition we have to put the value only up to the first section. So x is 0, this term becomes 0, plus c1 into x, x is 0, again this is 0, plus c2. So from the first boundary condition c2 comes out to be 0. So now here I have put the first boundary condition and found out the value of constant c2. Next I'll apply the second boundary condition. So therefore putting second boundary condition in equation second. So we have at x is equal to 9 meter, y is 0, so y becomes 0 in equation second. It's equal to, now x will be 9 meter, so this is 322 by 6, which is as it is. In place of x I'll write down 9, so 9 cube, then plus c1 into x, that is plus 9c1 because x is 9. Next c2 is 0, then minus 210 by 6 into bracket x minus 2, that is 9 minus 2 whole cube, then minus 125 by 6, x minus 6, that is 9 minus 6 cube, minus 26 by 24, x, that is 9 raised to 4. So here if I go on calculating this, simplifying this term, I'll get the answer of c1 as it comes out to be minus 2160.86. So here I have found out the value of c1. Previously c2 was calculated. The next thing would be putting the values in respective equation. So at first I'll put value of C1 in equation number 1 to get the slope equation. So after this, therefore, put C1 is equal to minus 2160.86 in equation number 1. I'll put the value onto the next page. So we have the first equation in which EI, it was dy by dx is equal to 322 by 2 x square, and then it was plus C1 is minus 2160.86, and the remaining terms I'll write them as it is. Now this is the equation. Therefore, I'll say that equation number 3 is called as the slope equation, and from this, slope at any given distance in the beam can be calculated. So from the slope equation we can see that x is the variable. We go on shifting different values of x depending on the length of the beam, at which section we have to calculate the slope, and we are going to find dy by dx, that is the slope value. Now the question here was to calculate the maximum slope. Yes, we have to find out maximum slope. Now for a simply supported beam, maximum slope occurs at each of the supports, that is either at A or at B. So first we will calculate at A. So here I'll say that therefore for maximum slope, put x is equal to 0 in equation number 3, because at the supports we have the maximum slope. So here we have, this will be EI, dy by dx will be maximum. Now I'll put x is equal to 0 in this equation. So the first term, that becomes 0 minus 2160.86. Here we have minus 210 by 2. Here if I put 0, this term is minus 2. So minus 2 square. So that becomes 4. Then minus 125 by 2. Here we have, if we put the 0, minus 6 square, that becomes 36. Then minus 26 by 6, x cube, x is 0, so the last term also becomes 0. So here I'll get this value of the maximum slope as it will be the maximum slope is minus 4830.86, and here we want dy by dx on one side, so therefore dy by dx, which is maximum, I'll send EI onto the other side, comes out to be minus 4830.86 upon EI. So this is the maximum slope. This is our first answer. Next, maximum slope will also occur when x is equal to 9 meter, that is at point B. So I'll say that again, for maximum slope, put x is equal to 9 meter in equation number 3. So we have, in equation 3 we have to put the value of x as 9 meter. So it is EI dy by dx maximum is equal to, the first term is 322 by 2, x that is 9 square minus 2160.86 minus 210 by 2 into 9 minus 2, that is 7, and 7 square. So here we have 9 minus 2, that becomes 7, 7 square, that is 49, then minus 125 by 2. Here we have 9 minus 6, that is 3, 3 square, that becomes 9, minus 26 by 6. Here we have 9 cube. So therefore EI into dy by dx maximum, I'll write the terms here. First of all, we have 322 by 2 into 9 square, that comes out to be 13041 minus 2160.86. Then we have 210 divided by 2 into 49, that comes out to be 5145, minus we have 125 divided by 2 into 9, that is 562.5, minus 9 cube into 26 divided by 6, that is 3159. So on simplifying this, here this will be, if I add up all the values, it comes out to be 2013.64. So therefore I'll shift EI onto the other side. So this is the maximum slope value which we are getting at point B, divided by EI. This is our second answer. So now, once we have found out the maximum slope, the next thing is we need to find out the deflection, and that is at the center, which is given in the problem. So in equation 2 we have deflection, which is y, but only thing is we have to put C1 C2 values in equation number 2. So here I'll say that therefore put C1 and C2 in equation number 2. So we have EI into y is equal to 322 by 6 x cube. It is plus C1 into x. Here we have, after the first term, plus C1 into x. C1 value is minus 2160.86. So I'll put it into x, plus C2 is 0, so no need to write this term. I'll directly copy all the terms here. Now this is equation number 4 for us. In equation 4 we have y as the deflection, x is the variable, so at any given distance x on the beam we can find the deflection. So therefore equation number 4 gives deflection equation, and from this deflection at any point in a beam can be calculated. So now if we look into the question, here they have mentioned that we have to find y, that is deflection at the center. So at the center, if we look at the length of the beam is 9 meter, length is 9 meter, and we have to find the deflection at the center, that is at 4.5 meter. So I'll say that therefore put x is equal to 4.5 meter in equation number 4. So here I'll put the values. This is 322 by 6. Here we have 4.5 cube minus 2160.86 into 4.5 minus 210 by 6 into 4.5 minus 2 cube minus 125 by 6, 4.5 minus 6 whole cube minus 26 by 24, 4.5 raised to power 4. So here on calculating this, I am getting my answer as it is minus 5754.29. Since we want the deflection y, it is at the center, that is equal to minus 5754.29. I'll shift EI onto the other side, so it comes in the denominator. Suppose in this problem, if EI value would have been given, we would have put the values and find the answer. But here, since EI is constant, I'll keep it as it is. So this is the deflection at the center, our third answer. And your negative sign indicates that the deflection of the beam is in the downward direction. And with this, we complete the problem.